Well, welcome. Thanks for joining us again today. We're here at another one of the Centrify Chalk Talk series with Paul Moore, our CTO. We're going to be talking a lot more in depth about our work that we've done on the Racoon IKE Daemon in the Linux platforms and some of the things we had to do in order to build our DirectSecure products.
As we saw in part one of the series, and this is part two, that one of the core components of the IPsec solution is an IKE daemon, which is the Internet Key Exchange daemon. And on the Linux platforms, and as we'll see later on Solaris as well, we decided to use Racoon as the platform to build the user mode components of our software.
And Racoon's the one that comes with Linux, is that right?
There's actually multiple different ones that come with various Linuxes. So there is a suite of IPsec user mode tools called the SWANs. Open SWAN and Free SWAN and Strong SWAN. They all come from a common code base and kind of got forked off into slightly different projects. There is then another project called Racoon, which also is roughly the same vintage as those things, but it's a completely separate code base from those. It's very typical of the fragmented world of many open source projects. You've got several different teams try doing various things, and then you get different teams kind of breaking up due to various, either they decided to focus on different technical areas, or sometimes there's a political infighting causes forks. Very similar to the various numbers of BSDs there are, for example. Sure. And what comes on some Linuxes, you'll see some of them have SWANs, varying SWANs. Some of them have Racoon, some of them have both. Certainly the SWAN code base is very good for VPNs, but as we talked about earlier on, we're looking for transport mode support here. And for various reasons, we decided to use Racoon as our starting point. One of the main reasons being because it has Kerberos support in it already, and we needed to have Kerberos support. Although that's a Microsoft extension, the Racoon team had implemented that. One of the main challenges for us is that we ship enterprise scale, commercial quality software to our customers, and it's the quality of the various open source code bases can vary a lot, and that's obviously not acceptable for us to really not know what we're doing.
And we don't want very many tech support calls, obviously. So
yes, the more you can clean up in advance, the better things are going to be. And also, if you can get the code base to a nice clean state, then you can hopefully keep it clean as you move forward, and you can avoid a whole bunch of problems down the line. So we use the same techniques that we use for our own code, and we're also dependent in direct control on other open source technologies, but which are very mature, like Kerberos and Open LDAP and so on. But this is the first time we've been presented with a whole new code base for some time. So we use two tools. The first tool we use is a tool called Coverity. Coverity is a commercial source code analyzer. So what that does is it reads the source code of the product and tries to follow the code path through it simply by reading the source code. It doesn't actually run the code. I mean, maybe in its head it runs the code, but it reads the source code and works out based on a rule base that it has looking for programming errors. And it's as I said, it's a commercial tool. It's not cheap, but this is not meant to be a commercial for Coverity, but it's certainly a very powerful tool, and finds lots and lots of very obscure bugs. I mean, it'll also find really stupid bugs as well, like you open a file and forget to close it and things like that. Those are the classic things it'll look for. And so we first of all made sure that code base was completely clean under Coverity, and that took actually a fair amount of time. There was a fair amount of issues with it. The other tool we used is a tool called Valgrind. And what Valgrind is this one is good. It's a free tool. This is a tool which actually emulates a CPU. It emulates an x86 processor running on an x86 processor and actually runs the whole program. So you just run it like it's a normal program, but it's run in this emulated processor, and it watches the code running and can detect all sorts of very sophisticated errors. Particularly if your code starts making decisions on uninitialized areas of memory. It knows in all of your memory that you're using which bits you've written to and which bits you're writing to, and so on. So it catches lots of very nasty bugs. When we first run a 5-minute session of Racoon under Valgrind, it came up with something like 13,000 errors, which is kind of a little bit alarming. It's interesting that most of those actually came down to two issues, neither of which were to do with the Racoon, to be fair. I mean, we did find lots of other things which were to Racoon, but the vast majority of them came from uninitialized memory reads in Open SSL and in Kerberos. So it actually identified a Kerberos error, and the Open SSL one was caused by, and this is, for anybody in the open source world, there's a very famous bug in OpenSSL that caused Debian, I think it was the Debian distribution of Linux, a problem that some engineer corrected a random number generator inside OpenSSL because it was using uninitialized memory, but in fact it was deliberately using uninitialized memory to introduce randomness into its random number generator. But of course Valgrind is going, wait a minute, you're reading uninitialized memory here. So that was the same situation we saw in that one. So that actually was a fair amount of work to get those two tools to declare the code clear. It found lots of pathways through where things would be allocated, not released, a lot of memory leaks, files not being closed, genuine bugs. Some of them, of course, were in very obscure pathways that would only be used if you're using some very obscure options, but some of them were actually in the mainstream code of it. So that we feel that having got it clean through those two pieces of technology, that we've actually got a very clean code base.
Those sound like more programming or coding bugs per se, right, as opposed to feature functionality that doesn't quite work right.
Right. So the very first thing was we'll take it warts and all, with the features as specified, and just get it so that the code itself is clean. Then the next thing we had to do was A, add some features, and B, correct some features which were advertised as working, but didn't actually work as advertised. So what I'm going to talk about now is some of the improvements we made for PKI support, some of the features we had to add. Okay. And this is not going to make sense unless you've seen the part one of this series, or some of it will still make sense. So this is my Racoon here. So this is, if you remember correctly, what we had was we said we have an IKE daemon, and so this is Racoon, right? The specific IKE daemon on Linux that we fixed. So the first thing we talked about was certificate support and how you should trust certificates. So if you remember correctly, what I said you get is a certificate. This is my diagram of a certificate here. Has a pointer to the person, the authority that issued it. Right. And this will identify a certificate authority, typically a certificate server that actually issued this certificate. And what we would normally do is we would take this certificate authority, the certificate of this certificate authority itself, and install it on the same machine as Racoon. So then when we receive a certificate, this one, we can see, we know this certificate, so we therefore can trust this because this guy points to this one. The problem with that in a large-scale enterprise deployments, let's say in the government, typically this isn't what you see. Typically, you'll see that then this certificate points to a higher level CA. So this may be, there's a chain of trust, right? And this one actually then points to some, so this is, let's say, the US government, right, certificate. There's a master server which issues certificates to an intermediate CA2 and intermediate CA1. So the certificate was actually issued by this guy, but there's a chain of trust which goes all the way up to this one here.
The guy who's typically self-signed.
This one is typically self-signed, yes. And what you would like to have to happen is that I would like to say on this Racoon here, on this system, that I trust anything issued by this, right? Because that's the policy we want to have. Anything issued by this root here, I trust. The problem with that is that if we just have this installed on here, and I receive this, unless I have these two, I don't know that I can't follow this chain all the way back to here. So that was the problem we were presented with in trying to resolve how to make this work. The solution is support for something called PKCS7. And what PKCS7 is rather than a packet being exchanged which just contains a certificate, it contains a set of certificates or a chain of certificates. So if you remember over here there's another machine over here. And what I do is, rather than just sending my certificate over, and remember there's also a mutual exchange coming back, rather than just sending my certificate over, what I do is I send a big PKCS7 collection, which actually has my cert, plus it has CA1 and CA2 and CA, and let's say the root in it, with all their pointers pointing to each other, like so. So actually what you do is you don't necessarily send over the entire chain, but you send over whatever bits of chain you've got, right?
Okay, enough to prove your point, which is my certificate should be trusted.
Right, and the idea is then, as long as this guy has in its list of trusts some link in this chain, then it will trust it. So it could have this one installed as a trust certificate, in which case it would be fine anyway because it was here. Or it could have this one installed, which is representing the entire enterprise root. And because it can see a valid chain coming all the way up through there, it knows then to trust the certificate it's seen. And that really makes things scale much better. So now some certificate authority I've never heard of in some department around the other side of the world, as long as ultimately I can follow that chain back, then it'll still work.
Yeah, because it's the alternative, I assume, would be if I only receive the certificate from machine X, I have to make a request to the URL for, issuer and go ask issuer, did you issue the certificate? Right, and ask issuer who issued you until I get to somebody I trust, if you didn't supply me the full set of data.
Well, you actually need the certificate because you need to verify that the certificate is valid as well, because you don't know whether you trust the people in between as well. So,
right.
So
but I mean, if let's say you only had the root certificate and I didn't have all the intermediaries.
So this is typically not a URL. This is typically a distinguished name. So it's not actually. In general, there's not a way you can go and get that online. That's why it's in this.
Maybe I'm confusing that with CRLs and OCCSP.
CRLs definitely, and that's further down here, and that's going to be our next topic. Is what some pointers further down. But these are typically CNs, distinguished names, ASN1 distinguished names, which. And by the way, so there's an obvious question. Well, wait a minute. How is it that I can send this chain over claiming to be issued by this, but I could be lying about that? So how do I know this chain is valid? And the reason I know this chain is valid is because this guy here has signed that. When he issued this is signed using the public key of this one here. So we can verify, and likewise, using the private key of this guy here. And likewise, this one has been, this one was signed by this guy, and this one was signed by this guy. So we can verify the signature of each one in step.
But ultimately, I still have to have one of those.
One of them I have to, yes, but what I'm saying is if I didn't have the signatures, if that signature chain wasn't there, just saying, honestly, I was signed by that. Just claiming to be signed by it isn't enough. What you actually have to do is verify the signature of this thing using the public key. Remember, a certificate is basically a decorated public key. So the public key is available, so everyone can check that it's a valid chain. So that was PKCS7 support. So what we had to do is both, when I send the certificate, when I initiate the thing, I have to send over my PKCS7 full chain, which also means that when there's another piece of, right, if you recall, we have the certificate requesting piece of software which went off to AD to request a certificate. When we request the certificate, what we actually request is a PKCS7 chain rather than just the certificate itself. So we actually end up with a complete chain of all the certificates between there and its root, or whatever it knows about, but in general, all of it. We then transmit it to the far side, and when we receive it now, we also have to then process the whole chain rather than just looking for a certificate and comparing it against a root cert. So that's a mandatory requirement for deployment into non-trivial certificate environments. So that was the first piece of work we did with regards to certificates. So the next thing we did, which you just mentioned a second ago, was to do with revocation checking. Right, which is, so again, if we have, here's a cert. So we got all this information. Another thing we have down here is a pointer to a CRL, and I'll say what that means in a second, and also possibly an OCCSP server. So a CRL is a certificate revocation list, which is basically a list of certs that I've declared dead.
Because a certificate authority issues certificates,
yes.
And if somebody were to leave the organization, machine leave the organization before their certificate expires, administrator goes in and revokes that certificate.
Right.
So it somehow has to be marked as bad so that other people don't trust it.
The point about it is that over here, this is our certificate server, is maintaining a list of revoked certificates. And inside the certificate list is a pointer back to one or either of either a certificate revocation list or an OCCSP server. We'll talk about certificate revocation lists first of all. So here we have revoked certificates. A CRL is basically a static mechanism that you are supposed to go and fetch the CRL. So this is let me just draw my Unix machine boundary here. So you're supposed to fetch the CRL into some local CRL store. And a CRL itself has an expiry date, a valid, from and to date.
And it's also been signed by the CA, right, to
yes.
prove that it hasn't been tampered with.
Yes. And so now what happens is that when I receive a certificate as a Racoon, what I have to do is verify in the CRL of the certificate that this hasn't been revoked or not. Now that code already existed. That's fairly standard code to just when you say, is this certificate valid? By the way, under the hood, Racoon is using OpenSSL to do all its crypto support. So there's already standard CRL support within OpenSSL. The problem is that the dynamics of managing the contents of the CRL were not really there. So we have a thing identifying the CRL that we want. We look in the CRL store, it's not there, right? So now we need to go and fetch it, right? Okay. And that can be an expensive operation in large certificate environments. There could be thousands or tens of thousands of revoked certificates. Right. And so you need to go and fetch that CRL from wherever, this is a URL. Right? Yes. Wherever that URL points, you need to go and fetch that information. And the question is, should you fetch it synchronously or should you fetch it asynchronously? And in general, you want to fetch it asynchronously. Although you can argue it either way, whether it should be fetched synchronously or asynchronously. In other words, should you have to wait to do that machine-to-machine authenticate while you go off and fetch this thing online? The other one is if it's expired, and I look at the list and it's expired or it's about to expire, I really ought to go and fetch a fresh copy, and that one definitely I should do asynchronously. So there's definitely work, again, to make it work on a big scale and to give yourselves crisp responses.
But the problem with this, I think you already said it, but the problem I understand with the CRL is that the size of that file, if you will, that I have to go get could be really big. Yes. And cost me a lot of time. Yes. With respect to logins and yes. access.
So AD actually makes some CRL information available early. And we can, for example, when we look, so here, this CRL I'm talking about here is I want to check a cert that's been given to me by another person. So a person gives me, I'm not checking my cert, I'm checking my remote correspondence cert. Right? There's a good heuristic, though, that I'm quite likely to see certificates from the same CA that I'm in, which means they'll have the same CRL as me. So what we do is, when we right at the beginning, when we issue a certificate to ourselves, one of the first things we do is we go and get a CRL for the CA we're part of, just assuming that that's a valuable thing to have, because probably a lot of the machines we talk to are going to have certificates from the same CA and therefore with the same CRL. So that's a kind of heuristic optimization, just to go and get that CRL. But if they're in a completely different division, with CAs issued from somewhere else, so this will be the first time we've seen that CRL. So there we have to decide whether to go and fetch it right now and wait while we get it, or whether we should just assume that it's okay this time, but the next time they try and do it, maybe we'll throw them. Remember, the certificate still has to be valid every other way. It's just whether it's being revoked or not. So a much better thing to use is this guy here, which is OCSP. Nice thing about OCSP is, by the way, I've just realized this is not right here. Since this is meant to be my UNIX system boundary, that's like that. So OCSP is a real-time tool. So we have effectively a web server, in fact it is a web server, fronting this list of revoked certs. And an OCSP is a protocol, online certificate status protocol, to go and read right now in real time the status of one particular certificate. So it requires a network round trip every time, but it's a very small network round trip. CRLs require one big network round trip, but then after that, they don't need any more network round trips. So if you have OCSP configured, and again, it's a configuration of your CA. The CA, typically, if you have an OCSP server, then your certificate server will be issuing certificates that say my OCSP server is over there. And so a big change we made to Racoon then is to look at the OCSP URL to see if it's present on a certificate. And if it is, it goes and talks directly to the OCSP server. In fact, it doesn't. It looks, first of all, to see if it has a CRL for it locally. And again, because there's trade-offs between, should I use the CRL first or should I use OCSP first? Yes. Because the CRL, if I've actually got the CRL, it's cheaper to do the CRL than to do OCSP. And in fact, we do multiple passes. We try what we think is the cheapest one first, and then we try the other way around just in case. So there's a lot of quite fiddly logic of prioritizing the CRL versus OCSP.
We've been talking about Active Directory infrastructures with the Microsoft CA. Does Microsoft CA offer an OCSP server?
Yes, yeah. That was introduced. There was a downloadable, I think, there's a downloadable OCSP server in Windows 2003 certificate server as a kind of later add-on. In 2008, it comes as standard. There's an OCSP, you just turn it on and it all works by magic.
Also on the CRLs, do I have to go back to the CA server itself to pick it up, or do the CRLs get published in the directory and then distributed so that I pick them up out of the directory?
It depends how you configure the CA. You can tell the CA which CRLs to publish, put in the certificate, and which CRLs to maintain. Whether they should be for a Windows one, they can either be an HTTP, LDAP, i.e. read them out directly out of AD, or a file share one. The only one we support is HTTP. Okay. Again, because we're using OpenSSL's CRL. The overall framework we're using, all the OCSP logic is actually inside OpenSSL, just like the CRL checking's inside OpenSSL. We're kind of just making sure we call the right bits of OpenSSL in the right order, and OpenSSL only supports HTTP. So that's basically the enhancements we made to the certificate handling. And as you can see, they're all to do with making things work reliably on an enterprise scale.
Absolutely, and seamlessly, so I don't have to worry about managing it.
Right. All of this works automatically. You don't have to. I mean, we obviously have. If you want to change the OCSP server or change the priorities between CRLs and OCSPs, you can do that kind of thing. But the default settings is to just make everything just work by magic as much as possible. So one of the reasons I said we chose Racoon was because we wanted to have Kerberos support. So if you remember, Kerberos support is all about, so we have over here machine A and machine B. And so here's our Racoon, our IKE daemon here. And it needs to ask for a service ticket. Sorry, it needs to ask for a service ticket from AD for the IKE service on machine B. And then there's some negotiation that goes backwards and forwards to mutually authenticate the two ends.
So it's a different ticket than the host ticket? Is it an IKE ticket? I mean, the name of the service.
I think it actually just asks for the host service over there. The point about it is that the Kerberos machine-to-machine authentication for IKE was defined by Microsoft. Microsoft implemented it within an AD environment, and it's published as an internet draft. I don't think it actually got to be a formal RFC. I think it got to be it's an informational draft. But the point is it's a Microsoft thing. But the Racoon team decided to implement that inside Racoon because they saw that it was a useful thing to do, although it's very unusual to see many Kerberos environments in the Unix environment before you would get direct control installed, obviously. However, they hadn't followed Microsoft's spec at all. So Racoon would interoperate with Racoon, but would not interoperate with with a Windows machine. And they'd made, there was two types of mistake. There was, first of all, where the spec just said, you know, this is what the packets should be that you exchange backwards and forwards, and they just missed bits out of the packets. And the second thing was that they thought they were paying attention to what the exchange should be, but in fact were making mistakes in it. Plus, also, there was actually some bugs in the implementation. The implementation leaked in various places and would crash in other places. You could see that it would never actually been used in a live environment, and certainly didn't interoperate with a Windows system. So actually trying to get that interoperation to work was actually quite an interesting challenge, because although Microsoft had documented the exchange, it wasn't very clearly, to be fair to the Racoon engineers, it wasn't very clearly documented. So that involved a lot of debugging deep down inside Windows code to find out why Windows was complaining about various things. But in the end, we managed to get that to work. So as I said, that's why we chose Racoon, was because of the Kerberos support there. And I would say that the code is still 80% of their original code, but there was a fair amount of cleaning and correcting of that work to be done. And the Kerberos requirement is what brings us to what's probably our last topic in this section, is the port to Solaris. So we wanted to try and bring Kerberos support to as many platforms as possible. And what that meant was that if the platform already had Kerberos, that was fine. But in fact, no Unix systems other than Racoon had it. So the solution for us was to therefore port Racoon to those platforms that we could do that on.
That means that Racoon was there for most of the Linux platforms.
Racoon runs on Linux platforms, yes. It actually would run on BSD as well, but you know, BSD is not in our set of supported platforms for direct control at all. So our main focus was Linux. So it's interesting to look at how we had to port it and what the challenges were with doing that, because that actually then shows you the heritage of some of the IPsec implementations on these various platforms. So if you remember, I drew a picture of, again, machine A, and we had the kernel to user space. And down here we had the TCP stack, and up here we had IPsec. And if you remember, I had IKE daemon here and some policy here. And these guys communicated like this. And if you're going to port these pieces of code to a different platform, since this is a different operating system here, the nature of this link here of how the kernel mode talks to the user mode can vary from different platform to from platform to platform. And actually one of the biggest challenges is, in fact, this is a bidirectional communication. This is fairly unusual that you'll see. Normally, it's the user programs asking the operating system to do things. In the case of IPsec, the kernel has to suddenly go, oh, wait a minute, I need to talk to machine B. I've got to do encryption to it. So therefore, it needs to call up to say, please do something for me. So this is actually a bidirectional communication that goes on here. And on Linux, this interface here started out, this interface started out with something called RFC 2367. You'd think I'd have that memorized now. And what that interface describes how the user mode components and the kernel mode components should communicate with each other. And that originally came from BSD. So this is some time ago. And it describes the runtime mechanisms whereby IPsec can say, oh, I need a key to do this, and how this guy can then say, yes, here's some keys for you, or get rid of this communication, and so on. What obviously happened later on was that this was extended by the Linux people to add more capabilities to it. What they needed was the ability to do control of the policy itself, to specify the rules. So they had to extend that. And likewise, they had to extend, the Solaris people also extended it to do the same thing, but they extended it in a different way. So the Linux set of extensions took this as the core, and they extended it to add, let's say, to double the amount of capability it had. The Solaris people also saw that they needed to have the same capabilities, but they did it in a completely different way. The nice thing about it is they all basically started from the same place, so it's roughly the same how it works. To contrast that with, let's say, other platforms, other well-known Unixes who have not based off this at all. So here, although they use different interfaces, they're kind of roughly in the same space. So what that meant that we had to do, when we ported Racoon over to Solaris, what we did we created a bridge component here, which actually runs in user space, which talks the Solaris interface, this extension here, and makes it look like this capability here. So when Racoon is running up here and talking to this bridge, it thinks it's talking to a Unix machine, sorry, to a Linux machine. Sure. It doesn't know any different. There's a slight change to make it realize that it has to talk to this bridge rather than talking through the kernel. In a similar way, the Solaris code thinks it's talking to Solaris components, whereas in fact it's talking indirectly through this bridge component. So that's, again, was a fairly major piece of effort to port that over. We're in the process of still investigating how we can do that on other platforms, such as HPUX, AIX, and so on, whether it's possible to use the same model to port that onto other platforms. But it was an interesting challenge to do that.
So a protocol translator, if you will.
Yes, yes, very, very similar. Basically takes packets in, munges them around a bit, and sends them back out again, and vice versa. There are actually a few capability differences between how the kernel works on the two different platforms. So we had to, it's more than just conversion. So for example, if somebody changes a policy in here, on a Linux box, an announcement comes out of the kernel saying somebody just changed a policy. And so Racoon expects to see the change announcements coming out. On a Solaris system, that doesn't happen. So we have to kind of mimic that happening. So if you actually look at the Racoon code base we have, there's very few places in there where it says, if it's Solaris, do that. It's probably, 10 or 20 lines of code changing. Yep. That's all.
So are the IPsec implementations down in that kernel space, so those provide roughly the same capabilities, and it's just a matter of the controls?
That's actually a very interesting question.
Because I imagine you get a lot of differences between the various platforms.
The Solaris one is very similar to the Linux one. And I'm not quite sure why they're so similar, because ultimately a lot of that probably originally all the work was done on BSD. And Solaris is heavily based on BSD. So that's probably why there's this common heritage and this common heritage of the RFC here. But there are some differences. One of the main differences, which is actually quite a significant one, which we can't do anything, some things we can fix with various bits of sleight of hand tricks we play. On Linux and on Windows, you can specify in a policy that I should try to make this communication encrypted, but if I can't make it encrypted, allow it to continue anyway. So that enables you to have it as part of your defense, but ultimately it's more important for my business for this database to be able to talk to that application server than it is to worry about whether the traffic's being encrypted or not. And there are times where that where some negotiation may fail. I got expired certificates, the domain controllers are offline, or whatever. In Windows and in Linux, you can say that. In Solaris, you can't say that. There is no way of saying this policy is optional. It's either got to be there, in which case you cannot do the communication unless you're fully obeying that policy. And in the discussions I had with the Solaris people about that, their view was, well, we don't even see how you could usefully implement an optional one. Yeah. That on other platforms, and again, it's so much of it is to do with the overall architecture of how that works. Our experience with other platforms, because we do have support for other platforms as well, is that they're quite different. Their capabilities are quite different in terms of what they can actually do and how they actually work.
So back to the failover thing, can you fail over from one method of authentication to another and continue on with encryption?
What we've been talking about here is IKE v1, and that has one major weakness, which is between the machine A and machine B will agree on an authentication mechanism to try. So if you support 3 mechanisms and I support 2, we'll eventually find a common one, or maybe even 2 common ones. But if we try the first one and it fails, we don't try anymore, which is actually a weakness of IKE v1. So Microsoft's kind of IKE follow-on to IKE v1, and also a set of RFCs in the pipeline called IKE v2, that's one of the main things that they address, is the ability to have cascading failover on the authentication mechanisms. And so, for example, if I'm configured to do Kerberos, and then if that Kerberos and PKI, if the Kerberos one fails, we won't try the PKI one instead. We'll just fail immediately, yes. And as I said, that's a big weakness.
Is that something that obviously is in the future for Linux, UNIX?
That's IKE v2.
Okay.
IKE v2. We're getting an interesting question now into because one of our major interop partners is Microsoft. So of course, what we would need to support is dictated to some extent by what Microsoft does, not only by what other Unix systems do. And it's not clear what Microsoft's attitude towards IKE v2 is going to be. Today, they have a thing called Auth IP, which is an equivalent to IKE v2 in that it resolves most of the issues that are there in IKE v1. But it's a Microsoft thing. It's which is not being pursued by other platforms.
Okay. I guess sort of a follow-on question is, in talking about Microsoft and what they're doing is, the new Windows 7 and the direct access. Is it using IPsec?
Yes, so direct access uses IPsec and IPv6 to make a very seamless experience of on the net and off the net on your corporate network when you're at home. You're always on your corporate network, even though you're in a hotel room.
Yeah. Well, I know their primary goal was to make it easier for the user to use corporate services. I'm just wondering about using a Windows 7 as the client to hit, let's say a Unix Linux server that.
Yeah, this will just work fine because So for example, our stuff supports IPv4 and IPv6, and it'll work fine, and we will enable you to do end-to-end encryption all the way from the Windows 7 client all the way up to the non-Windows server. That'll work fine.
Well, thanks, Paul, for that. This is one of our Chalk Talks on DirectSecure, Part 2, Technical Deep Dive. Again, Part 1 is available on the website, and we have a lot of other Chalk Talks available as well. Thank you for joining us today.